Okay, so let me continue with page 3, the second slide. We're going to have to graph a new function for you that is called greatest integer function. So let me just go over the definition of greatest integer. The symbols are going to be brackets that have an extra line on them. So and it's called greatest integer. So for any number, for example, greatest integer of -2, what does that mean? If we have numbers on the number line and we know where each number belongs to, if this is the 0, then the -2 is over here. So the greatest integer of -2 is going to be actually -2, which means that's the biggest integer to the left of -2, or itself when you have an integer. So for example, greatest integer of 2 is just 2, greatest integer of 0 is just 0, because the number that we're finding the greatest integer of is actually an integer. So it's itself every single time you have an integer. What happens when they are decimals? When they are decimals, then you have to know whether they are positive or negative, where they are on the number line. -2.5 is a number right here. So the greatest integer for -2.5, meaning the greatest integer that this number is bigger than, is actually -3, because that's the first integer to the left of the number -2.5. So -2.5 is actual number that is bigger than -3, and -3 is the greatest integer to the left of -2.5. So the greatest integer of -2.5 is -3. Now, what would be the greatest integer of 2.5? If this is the number 2, 2.5 is right here. So the greatest integer, again, to the left of 2.5 is the number 2. So you can see that this is not definitely absolute value. If you have the greatest integer of opposite numbers, it doesn't mean that you're going to have the answers as being opposite. So you have to be always careful when you find the greatest integer of anything. So on your slide, you have the greatest integer of 2 is 2, greatest integer of 2.3, that's only the number 2. Even if the number is very close to 2, 1.9999, still the greatest integer is 1, because this is not quite 2. So 2 is still bigger than this number, so the greatest integer is only 1. This number is definitely a little bit bigger than 0, but it's not quite 1, so the greatest integer is 0. This number, be careful with negatives, please. This is -3, this is -4, -3.5 is in between, so the greatest integer is -4. And -0.5 is -1, again for the same reason. This is 0, this is -1, this is where -0.5 lives, so the integer to the left of -0.5 is -1. So how do we graph a function like this? It's going to have a very funny shape, and then let's try to figure out some numbers. So if I'm writing a table of values where I have -2, -1, 0, 1, and 2, because those are usually the numbers that you pick whenever you have a table of values. Greatest integer of -2, and we went over this, is going to be simply -2. Greatest integer of -1 is going to be -1. Greatest integer of 0 is 0. Greatest integer of 1 is 1, and greatest integer of 2 is 2. When I plot those values, then it looks like it's going to form a straight line. But that's not going to be the case, and we're going to talk about that in a minute. What happens if my x, instead of being integers, I'm going to do it on the other side, and I have values -1.1, -1.2, -1.3, -1.4, and I can have any single value between -2 and -1. The greatest integers is still going to be -2. So it's actually going to work out as a mini line between -2 and -1, straight, because the greatest integer is -2 for all those numbers. But then when it gets to -1, it's going to jump to -1. So the way that I want to show you that this is possible and it's still being a function, when x is -1, the greatest integer is -1 and not -2 anymore, not -2. So the way to indicate that is that at this point it's going to be an open circle. So if this is the graph of f, there is no doubt that to graph this graph being f of -1, -1 and not -2, the same thing is going to happen between -1 and 0. So it's going to be constant until it hits the point of 0. That's where it's open. And then f of 0 is 0. So this point is closed, constant, and then open. And it's going to jump. It's going to be closed, constant, and then open. Close, constant, and open. Close, constant, and open. Close, constant, and open. And you can extend this graph beyond your table of values. So greatest integer function, it is a piecewise function because you have little pieces that form the entire function, but another name that it's given is a step function because it actually looks like little steps. And so in example 7, we have to graph this function, and it says the cost of a long distance phone call is 69 cents for the first minute, and then 58 cents for each additional minute or part of a minute. So this part right here in the problem is an indication that we're using a step function to graph this, and it's not going to be a straight line, it's going to be little pieces. And it's because you're going to pay 58 cents for each additional minute, even if you take an extra second. If you take an extra second or an extra 15 seconds or 30 seconds, you're still going to pay 58 cents for that entire minute. I'm going to use graph paper just because I can. If I'm using a table of values now, if this is T and this is C, the cost of this phone call, you can see how T is not going to be a single number, but T could be any number between 0 and 1. So for that first minute, you are paying 69 cents. So between 0 and 1, I am paying 69 cents, and it's a constant value. Now, after the first minute, the very first second into the second minute, you're going to pay 58 cents more. So I calculated that this is $1.27, and that's going to be the same anytime you're taking between 1 and 2 minutes. So that's why time in here is strictly greater than 1 and not greater than or equal. So it's open right here, and then it's closed. So unlike the original greatest integer function, this one first is open and then it's closed, but that's okay. We're being consequent with what the problem says. If you're taking 2 minutes, you're exactly paying this amount. Anytime more than 2 minutes, then it's going to make you jump to the next minute. So I'm adding again 58 cents to this amount, and we get $1.85 between 2 and 3. So between 2 and 3, $1.85. And then between the minute 3 and 4, we jump the $2 mark. So between 3 and 4, it's $2.43. And then between 4 and 5, we are paying more than $3 over here. It doesn't have to be exact. Some approximation is fine. And then between 5 and 6 minutes, I'm paying $3.59. So that is just to show you that there are real problems in life where we have a piecewise function or a step function to actually model the situation. This test for functions is actually going back to the definition of a function. Remember, a function is defined as having 2 sets of values for every input from the domain. You have only one output. If you have the graph of f, that means that for every single vertical line that you may graph, you're only touching the graph once. What happens here on this graph? For this vertical line, this particular x right here has 2 different y's, this y and this y. So y1 and y2. So for example, for this particular x, for this input, I'm giving 2 values of output. So this is not a function. Now, it doesn't have to be a bunch of vertical lines that have to have that property. It's only enough for the function to have one of them for it not to be a function. So in this example, they are saying, let's say that you have a vertical line at the value a. A could be any number, -3 or 2.5 or pi, for which you have 2 points that have x coordinate a, and then you have 2 different y values for it. So when one input has 2 different y values, that means that this is not a function. So this is called the vertical line test, because you are drawing vertical lines along the function just to check whether the function is being intersected more than once. If it is, then this is not the graph of a function. In here, this is the graph of a function because we're only intersecting once every single time. That's why it's important that you remember when we are graphing greatest integer function, if you have to have it like this, if you're closing for, I don't know, for example, x equals 1, if you're closing at 1 in both pieces, then that means that this x equals 1 has 2 y's, and you don't want to say that. That's why it is important that on the graph, one of these points is actually open, just to make sure you're indicating that when x is 1, there is only one value of y associated to it and not 2 values. This one is done for you, but let's just go over to see if you understood. It says, using the vertical line test, we see that the curves in part B and C represent functions, and the parts in A and D do not. So for example, in here, this vertical line is good enough to show that this is not a function, because for this x, you have 2 y's. And so for this one, in this one, it's even worse because you have 3 different y values. But you know, this one is worse, but either one of them is not a function. Now in here, I know that some people may think that we are not passing the vertical line test because it's kind of wavy. But if you draw only vertical lines rather than slanted lines or horizontal lines, you're only touching the graph once, and you can see that. In this case, it's also the same. Every single vertical line is touching the graph only once. Even when you graph a parabola that is very skewed, like, I don't know, x to the 10th power, I know that the graph kind of goes like this, but this doesn't mean that it's violating the vertical line test, because this continues growing. It kind of looks like a vertical line, but it's not. It just means that it's growing very fast. So this is also a function, and it passes the vertical line test. Every vertical line test is only intersecting the graph once. For every x, there is only one y and not 2. Now on example 9, we have, does the equation define y as a function of x? So in here, you have to solve for y. So to solve for y, part A, I just have to add x squared both sides. So you have y equals 2 plus x squared. So every single x is going to give you 1 y. So this is a function. Y is a function of f, of x. Now in part B, when we solve for y, we have x squared plus y squared equals 4. I have to subtract x squared from both sides, and I have y squared equals 4 minus x squared. And remember, when I'm solving for y and I'm taking the square root, when you take the square root on the other side, remember to put plus minus. So every x is actually giving you a positive y and a negative y. So in here, we're getting 2 y values. So this is y is not a function of x. And the last slides, they just give you general shape for several functions so that you have an idea how they're supposed to look like, so that when you graph the sketch and you don't see a general form, that means that you have to add more values to your table of values. For example, if you're graphing a parabola and you only have points going this way, then you know that you have to add more x's to your table of values so that you can obtain the actual shape of a parabola. The other thing that is showing you is that whenever we have even powers, it looks like a parabola, and whenever we have odd powers, it looks like a snake. The root functions, they look like a parabola on the side, but only one branch. So this is the square root of x. This is the fourth root of x. So for whenever we have an even root, it's just going to look like half of a parabola to the side. And when we have a cubic root of x or a fifth root of x or any odd root of x, it's going to look like a snake, but it's going to look laying down on the side. It's going to look like the letter S. The other general shapes that you should be aware of are reciprocal functions. When I have 1 over x, then the graph looks like it has two pieces, and one is on the first quadrant and the other one is on the third quadrant. And then when I have 1 over x squared, both pieces, one of them is on the first quadrant and the other one is on the second quadrant. Absolute value function, it looks like a V, and the greatest integer function, it looks like a steps, where I have a closed endpoint and an open endpoint to the right side.